welcome you to this series of lectures on marine hydrodynamics. Today is the 18th lecture in the series, and we will talk today about motion of cylinders in a fluid, particularly when the fluid is infinitely extended. So, in this the cylinder will emphasize as if the cylinder as it is a circular cylinder of radius a, and the fluid is infinitely extended. So, two aspects of the problem: when the cylinder is fixed, the fluid is moving, fluid is flowing. The second part is, suppose the cylinder is moving whereas the fluid is at rest at infinity. So, these two cases we will consider, then we will consider the rather it is a kind of repetition of what I have done, the uniform flow past a cylinder and also the uniform flow past a cylinder in the presence of circulation. So, this will be give us a very good idea about how the flow, there is a fluid flowing and there is an object. When the object is moving, what happens, and when the fluid is moving, what happens. So, that will give us a clear idea, because this kind of flow pattern is commonly observed in various, while dealing with various problems of marine hydrodynamics, because of it is a kind of give us an insight to the flow characteristics. So, first we will start with the motion of a cylinder in a fluid in this series. Motion of a circular cylinder. This approach I will take a very general approach. So, here what we want to study is, suppose I have a circular cylinder of radius a. I am considering a circular cylinder, it is moving with velocity a and velocity u, that is along x axis, and radius of the cylinder is a, and the fluid is infinitely extended. The fluid is infinitely extended, and which is at rest at infinity. Okay. So, since I have a cylinder inside a fluid, so what will happen to me? So, I am considering the fluid is inviscid, incompressible, fluid is inviscid, incompressible, and for a rotational motion, the motion is rotational, then we know that we will have del square phi is 0. This can be achieved in two ways, but I approach in a standard general way. Del square phi is 0 in the fluid region, and in the cylindrical polar coordinate in two dimension, like x is equal to r cos theta and y is equal to r sin theta, then what will happen to my Laplace equation? This will give me 1 by r del by del r, this is r del phi by del r plus 1 by r square del square phi by del theta square 0. Once this is 0, what will happen? So, as a result, what I will do, because I want to solve this equation, if I have to solve this equation, my simple approach is, suppose I take phi r theta is r into r is a function of r, capital theta upon theta. If I do this, then I can easily get it. What I will get, I will get easily that r doubles r into plus 1 by r prime r minus n square by r square, r of r is 0 and theta double prime plus n square theta is equal to 0. So, here what I have done, this I obtain individual equation by substituting, where n can be, n is an integer. So, that gives me my r of r is a cos n theta plus b sin n theta, sorry, theta of theta is a cos n theta plus this equation solution of this, and then if I look at the solution of this, that will give me, this will be, one can easily see that r of r will be, it is a kind of Euler type equation. So, you will get it, r of r is r to the power n. One can see that this is satisfied. So, n is integer, if n is not equal to 0, then it can be positive or negative. So, I can get my phi of r theta is of this form, a cos n theta plus r to the power plus minus n plus b sin n theta r to the power plus minus n. So, this is this I put it. So, this is here a b are arbitrary constant. So, for various values of n, I can choose any n, and so accordingly depending on n I can get a one of the solution, but this is the most general solution in the Cartesian coordinate in 2 dimension. Now, what are the boundaries? Suppose I say that I have a cylinder which is moving with the speed u in the x direction, then what will happen to my boundary conditions? If I have a cylinder, the cylinder is moving with speed u in the x direction, then I will have del phi by del r at r is equal to a, it will be minus u cos theta, because if it is, this is any point on the surface of the cylinder r theta, then if theta is the angle, this is the u component, then del phi by del r will give you r is equal to a is minus u cos theta, and that is, so here I will have the speed will be u cos theta at this point, and then, so since I am talking of a fluid which is at rest at infinity, that means my velocity component at my del phi by del r, this is 1. So, again this is because the cylinder is moving with the speed u in the horizontal direction, that gives me this, and when I go to the second condition, that means the fluid is at rest at infinity, that gives me del phi by del r at r is equal to infinity is 0, and which also I can put it in terms of 1 by r del phi by del theta, because these are the two components of velocity at r is equal to infinity will be 0. So, I have to solve this velocity potential phi subject to these two conditions to get the corresponding velocity potential, and once I get the velocity potential, then I will be able to find out what is w, because I can find psi and then I can find what is the compressed potential. So, now from A and B, from the nature of the solution of the boundary condition, I can always choose my phi r theta, because I have given a general solution phi r theta. If I choose is a r plus b by r cos theta, This can be one of the solution out of the many solutions possible when n is equal to, I have taken for the first part n is 1, whereas for the second part of the solution I have taken n is -1 and one of the, because out of, as I said, that depending on the nature, and it will be obvious afterwards that why I have chosen this form of the solution, because then what will happen to del phi by del r? I have to apply the two boundary condition, del phi by del r at r is equal to a will be a minus b by r square into cos theta, that is at r is equal to a, and this itself gives me minus u cos theta, and what is the left side gives me? That means a minus b by a square into cos theta. If this is u cos theta, that gives me a minus b by a square is equal to u. Sorry, there is a minus a minus b square by r del phi by del r a minus, okay, okay. Why I have, just a minute. Okay, so this is u cos theta, sorry, because I have taken del phi by del r, del phi by del r, del phi by del r, okay, I will clarify, that is u cos theta, not minus, and this is, it will be clear. So then what will happen? Then the second condition gives me, that is first condition gives me minus b by a square is equal to u, that is suppose one of the condition, and then the other condition I got, I have del phi by del r at r is equal to infinity equal to a cos theta del phi by del r at a cos theta, and that is 0, which implies a is 0, and if a is 0, then that gives me, okay, so this is actually minus b cos theta, this is minus, this is fine, so this will be minus, my a is 0, so which implies my b is equal to u a square, and this is a, okay, now it is clear, there is no problem, this assumption is clear. So then what will happen, my phi will be a square u by r, because this is my phi theta, so my phi will be, from these two I will have phi is equal to a square, because a is 0, so u a square by r into cos theta. This is the velocity potential. Once my phi I obtained, then what will be my psi? Then what will be my del phi by del r? Del phi by del r is nothing but 1 by r del psi by del theta, and that itself gives you minus a square by r square u cos theta, and that gives me my del psi by del theta minus a square u by r cos theta, which gives my psi is equal to minus a square u by r sin theta, and one psi is this, then my w will be, this is the complex potential, phi plus I psi, and that it gives me, because my phi is a square u by r cos theta minus a square u by r sin theta, which is nothing but a square u by r into e to the minus I theta, which I can call it as a square u by r e to the power I theta square u by z. So, this is my W. So, the complex potential when I have a uniform flow, here what I have considered, my flow at infinity is 0, there is no flow at infinity, the fluid is at rest at infinity, and on the boundary the cylinder is moving with a speed u in the x direction. In that case, the complex velocity potential W becomes this. Now, if you look at this, we know that in case of a doublet, W is equal to mu by z. If W is equal to mu by z, this is the complex potential for a doublet. So, the flow when there is a, so in this case what is happening in the case of a cylinder which is moving at a speed u, if mu becomes a square u, then the doublet is reducing to this flow pattern. So, that is a very common thing between a doublet and a cylinder, motion of a cylinder in a fluid which is at rest at infinity. So, this is the most general case of the complex potential. Now, with this let me analyze what is happening to the energy associated with the flow. So, basically if you look at the kinetic energy, because this will give us a very interesting result, the kinetic energy if I call it as T, that will be 1 by 2 rho integral over this. I had done it earlier, but let me just repeat it, q square d tau, and this can be written as minus rho by 2. I have done this in one of the earlier lecture by using the Green's theorem. This can be written phi del phi by del n ds. This is the kinetic energy in a particular confined region with the volume tau whose surface area is S. Now, we know that phi is equal to, in our case, in case of cylinder, we know phi is equal to u a square by r cos theta. So, we have, and also we know what is del phi by del r. Del phi by del r at r is equal to a is minus u cos theta. Then what will happen? If I assume this is the general definition of T, the kinetic energy, and in our case phi, if phi is equal to this, then we know that del phi by del r on r is equal to a is this. Then what will happen? Suppose I assume that let T1 be the kinetic energy of the liquid on the boundary of the cylinder. Okay. And let T2 be the, because the cylinder is moving, is the kinetic energy of the cylinder, because the cylinder is moving, this is the kinetic energy of the cylinder, and T1 is the kinetic energy of the liquid on the boundary of the cylinder. If I say sigma is the density of the cylinder, and I say rho density of the fluid, this is the density of the fluid, then what will happen to T1? Then my T1 will be minus rho by 2 integral over S phi del phi by del n ds, and since this is the on the boundary of the cylinder. So, on the boundary of the cylinder what will be, this will be, if I calculate it as r is equal to a. So, this will be say r is equal to a. So, this I can write it as minus rho by 2 integral 0 to 2 pi, because I have a cylinder of radius a and r is equal to a. So, this will be, so basically this will give me phi del phi by del r is equal to a into a d theta, because on the boundary of the cylinder I am calculating, and this will give me minus rho by 2 0 to 2 pi, this is square by r is a. So, this is into cos theta into minus u cos theta a d theta. If I do this calculation, then it gives me very simple. I will get it, if I simplify this, I can easily get it minus rho by 2, rather minus plus rho by 2, this is a is there, that is a is cancel, and that will give me u square a square, and then 0 to 2 pi I have cos square theta d theta, and that will give me rho u square a square by 4. If I put it 0 to 2 pi 1 plus cos 2 theta d theta, and then I will have rho u square a square by 4 into 2 pi, and that will give me rho pi a square into u square by 2, and I can call it half m prime u square. Here my m prime I put where my m prime equal to rho pi a square. And what is this? If I look at rho pi a square, this is nothing but I have a 2-dimensional cylinder. So, this m prime is rho pi a square, is nothing but the mass of the liquid displaced by the cylinder. I can call this. So, this is my T prime, T1. Now, if I look at the kinetic energy of the cylinder, because the cylinder is moving with speed u, and if I call m is the mass of the cylinder, then that will give me T2 half m u square, because u is the speed of the cylinder and m is the mass of the cylinder. Then, so hence the total kinetic energy of the cylinder and the fluid and the liquid fluid will be half m plus m prime into u square. This becomes the total kinetic energy of the cylinder and the fluid. Now, by energy equation, by equation of energy, the rate of change of total energy, it gives me rate of change of energy rate of change of total energy is same as the rate at which work done rate at which work is being done by external forces. External forces are at the boundary. Then if I apply this to this equation I will apply to this case of the cylinder, then I will have d by dt of the kinetic energy is equal to, basically this is work done per time, per unit time, and this is work done per unit time, and work done is nothing but force into distance. It is a very standard definition by time, and which I can write it as force into velocity. And if that is the case, then what is my d by dt? The total kinetic energy is, I have d by dt of half of m plus m prime into u square, and that is force is, if I call the force as F, total external force F, and then u is the velocity. So, that gives me, I simplify this gives me m plus m prime into u du by dt, this is equal to F into u, and that gives me my F as m plus m prime into du by dt. So, which I can also write F minus m prime du by dt is equal to m du by dt. So, one of these form I can write. So, what is happening here? So, F minus m prime du by dt is m du by dt. M du by dt is the kinetic energy, the total energy that is acting on the force that is acting on the per unit time. This is the force acting on the cylinder, and this is what is happening here is the total external force minus this m prime is the mass displaced, because this is associated with the displaced mass. So, what it says that the cylinder is experiencing a resistance to its motion. And what is the amount of the resistance? Of amount m prime du by dt per unit thickness. Per unit thickness due to the presence of the fluid. To the presence of the fluid. So, this is the resistance it is experiencing due to the presence of the fluid, and in this case, so in the process, and this is what with this let me say. So, in the process the mass of the, I will define another term what is called virtual mass in this context. So, the equation I will say that F is equal to F minus m prime du by dt equal to m du by dt. I will just write it again. So, what is happening, or I call it F equal to m plus m prime du by dt. When I say this, that means the mass m of the cylinder, m is the mass of the cylinder, and that is increased to m plus m prime when the cylinder is inside the fluid, and this mass and m prime is nothing but the mass of the liquid displaced, and this m plus m plus m prime, this m plus m prime together, this is called the virtual mass, because the mass of the cylinder is this, but when the fluid is, the cylinder is inside the fluid, the mass is increasing, which is moving with the fluid. So, m plus m prime is the virtual mass, and this is obtained by increasing the mass of the cylinder by the added mass, and the added mass, that is the m prime, and this m prime I call this is the added mass, or we sometimes call this the hydrodynamic mass. So, in the case of the circular cylinder of radius a, when this is, so for the circular cylinder of radius a, the added mass, the hydrodynamic mass is m prime, and m prime is equal to pi rho a square. This is, so it is clear that this is total is called the virtual mass, m plus m prime, this is called the virtual mass, and m prime is called the added mass. So, in fact, this is very important in the context of problems of marine hydrodynamics, because almost all marine hydrodynamics, when a body is moving in a fluid or a body is submerged in a fluid and forces are acting on it, there are resistances due to the fluid, and in the process, particularly for all moving body, it is very important, because the fluid, when the body will move, an amount of fluid will be always associated with that, and that is the amount of fluid that is associated, basically the amount of fluid that is displaced by the body, and then this amount of fluid always this is provides a resistance, and then this plays a very significant role in the almost calculation of force, or the force calculation on a body, and also this is the resistance calculation, this is always taken into account. And in this, the added mass coefficient, the hydrodynamic mass or the added mass is plays a very significant role. In fact, this added mass, the virtual mass for almost all marine structure, the virtual mass is, this is of this form, m plus k into m prime is the general nature of the virtual mass in almost all hydrodynamics problem. And this m prime is the added mass, where k is a constant which depends on the nature or depends on the structure, on the shape of the structure. The shape of the structure, and this is the general form of the virtual mass. Now, with this understanding, I will just calculate what happens when a cylinder is falling under gravity, because it is when it is falling under gravity, we say it is like fluid is the air, and let me just say that will falling under gravity. From this general form of the equation, we can easily find out. Suppose I have a cylinder of radius a, sorry. Suppose I have a cylinder of radius a, circular cylinder of radius a, and density sigma. This is about the cylinder. Cylinder is of radius and density sigma and is falling, whose axis is horizontal. I will say the axis of the cylinder axis remains horizontal, and it is in a fluid of density rho, fluid density is rho. And we consider an unit length of the cylinder, which is limited to two smooth vertical walls. Basically, these are the two walls. So, the cylinder is falling, and then what is the weight of the cylinder? Weight of cylinder, the weight of the cylinder will be pi a square sigma into g. Then what is the fluid upthrust? Upthrust of the liquid, look will be pi a square rho g. So, if this is the upthrust and this is the weight of the cylinder, because this is coming, it is always trying to bring the cylinder down, whereas the upthrust is trying to push it up. So, then what is the vertical downward force? Total vertical downward force, vertical downward force on the cylinder will be pi a square to sigma minus g, because sigma minus rho into g. If I consider y is the vertical displacement, vertical depth, or sometimes we call the vertical depth measured from the surface, at any instant of time. Then I will have from equation of motion pi a square sigma, this is the, because sigma is the density of the cylinder, pi a square sigma into dy by dt, d square y by dt square is equal to pi a square, this is the downward force, pi a square sigma minus rho into g minus pi, this is just by the presently a square rho a square y by dt square. This is coming exactly from the recently derived equation, because when a body is moving, because in a fluid, so this will be the equation just we have derived the, and this will give us, if we simplify this square y by dt square will give us sigma minus rho by sigma plus rho into g. This is the equation of the cylinder, and the cylinder is falling under the action of gravity. And here we have seen that in a fluid particularly, and we have seen from this equation that the cylinder depends on this, if y is large enough, sorry, rather what will happen, so what will happen if the cylinder will always will fall with the constant, with this constant acceleration, provided y is large. provided y is large enough for the surface condition to be negligible. So, in that case, because that means we have no condition on the surface of the cylinder, because y is so large that the surface condition we always can be neglected, the condition that is on the surface will be on the surface of the cylinder of the can be easily neglected. If we neglect the surface condition, then this will be the equation d square y by dt square is sigma minus rho minus sigma plus rho into g. Now, what will happen in case of a balloon? In case of a balloon which is moving in the upward direction, then it has to be sigma is always less than rho, and that is why if sigma is less than rho, then d square y. So, this there is upthrust, and in the process the cylinder moves in the upward direction. And on the other hand, in case of any other object sigma, where the sigma is greater than rho, then this will move up. On the other hand, in case of a stone or a heavy object, the body falls down. Even if we have a fluid. Now, with this same concept, what we have learned that when we have a cylinder body is moving in a fluid, so we have always experiences external force and always experiences a resistance. And again we have seen that when a cylinder falls under the action of gravity, always there is a upthrust, and unless it crosses this upthrust, then it will move in the upward direction, because gravity is trying to pull it in downward direction, whereas the upthrust will be, it is always acting in the upward direction. So, in the process usually move up in the case of a balloon. On the other hand, when in case of a heavy object, it always moves down in the downward direction. Now, I will just give a general condition for a cylinder moving on in an unbounded fluid. If a cylinder is moving in an unbounded fluid liquid, and suppose I assume the liquid is at rest at infinity, So, if I say the liquid is at rest at infinity, I can always say the velocity motion of the cylinder, the disturbances on the motion of the cylinder if the liquid is at rest at infinity, the disturbances at far field is negligible. Far field means I always mean that far from the object is far field is negligible. So, in that case dw by dz will be 0 at far field. If dw by dz is 0 for large values of z, for large z, the cylinder is reduced shape, it is. So, because of this, what we can, the most general form of the, in that case what will happen, I can, if I write w is equal to ik log z plus a1 by z plus a2 by z square plus this, and if I just say k is the, where k is the strength of circulation. there is no source and sink, because then k is the star. So, this will be gives me, that will give me dw by dz ik by z minus a 1 by z square minus a 2 by z cube 2 a 2 by z cube, so on. And it can be seen that here the motion fluid velocity is 0, as dw by dz will turn to 0 as z turns infinity. So, because of this form, in the most general form of a cylinder moving in an unbounded fluid which is at rest at infinity. So, I always can say, if suppose in addition, if I say the flow is uniform, suppose I say there is a uniform flow when the cylinder is moving, if there is a uniform flow, this is another case. Note, if there is a uniform flow along x axis with speed u, then the general motion can be w, can be u z plus I k log z plus a 1 by z plus a 2 by z square plus so on. And when there is no uniform flow, this gives me the motion when there is no flow at infinity, a fluid is at rest at infinity. On the other hand, when there is a uniform flow along the x axis which moves with the speed u along the x axis, then this will be the most general form of the complex potential. Now, I will just give a little hints about if I have a. So, from this I can easily get streaming and circulation about a fixed cylinder. When I have a, I already know that for flow past a cylinder, when there is a uniform flow which moves with whose speed is u at infinity in the horizontal direction, then my w is u z plus u a square by z. And if I have introduced a circulation of strength k, then my potential another term will be added, I k by 2 pi log z. So, this will be the complex potential for the uniform flow, a streaming motion as well as circulation about a fixed cylinder. And from here we can easily see that if we can easily find out del phi by del r in this case is u into 1 minus a square by r square cos theta, and my 1 by r del phi by del theta is minus u into 1 plus a square by r square into sin theta minus k by 2 pi r, and in that, so we can always get q square is equal to 2 u sin theta. So, rather I will say q square at r is equal to a, I will get a 2 u sin theta plus k by 2 pi a k by 2 pi a square, and hence what will happen, which implies q on the boundary of the cylinder will be 2 u sin theta plus k by 2 pi a. So, for theta is equal to, if I substitute here theta is equal to pi by 2, then my sin theta will be 1 and which will implies my Q max I will get 2 u plus k by 2 pi a. This will give me the maximum speed on the surface of the cylinder, and that will observe only at theta is equal to pi by 2 in the presence of circulation. On the other hand, what will happen by on the other hand we will see q is equal to 0 for sin theta is equal to minus k by 4 pi a u, and this gives the condition for, in fact q is 0. So, this gives the condition for stagnation point. This is the condition for stagnation. Condition for stagnation point. So, what we will see that when k is equal to 0, if there is no circulation, that means theta is equal to 0 or pi, and in that case we have a stagnation point. Earlier what we have seen in case of a uniform flow past a cylinder. Again, if we will go by apply Blasius theorem, because we have W, if we apply the Blasius theorem, we can get x minus I y integral dw by dz across the cylinder, and you can easily see that this will be minus I k rho u, and that will give us x is equal to 0 and y is k rho u. So, what it says that in the presence of circulation there is no drag force, which implies no drag force, but there is a resistance, and this resistance is k rho u, and that is rather there is a lift force, and this becomes this is k rho u. So, the cylinder experiences a lift force of magnitude k rho u, whereas there is no drag force that is experienced by the cylinder in the presence of circulation. And here, so this concept is very good to analyze the lift force. However, as we have already talked that this will not talk any detail about the drag force, because it is as we have explained it, which is clearer, because for a in viscid flow it will be difficult to find the drag force by using the, because the drag force will not be there because of the flow is in viscid, and that already has been explained in the while and talking about the when we have talked about the D'Alembert's paradox. On the other hand, this will be give a almost a realization about the lift force that is acting on the cylinder, and in fact this concept was used when we have talked very well about the lift calculation in case of a aerofoil, and this is all I want to tell about the motion of a circular cylinder today. Thank you very much.